name's Ray. I'm a rising sophomore in high school, and this is a video on a basic complete search problem. It's rated normal on the USACO guide. And yeah. Also, I'm in USACO Gold currently. Yeah. Okay. So this problem is from the 2017 February contest on the bronze division. It's called "Why Did the Cow Cross the Road Too?" Um, so you can pause and go through the problem statement. So anyway, the problem is the layout of Farmer John is basically his farm. So the layout of his farm is peculiar and has a large circular road running around the perimeter of the main field, and his cows graze on that field during the day. Every morning, the cows cross into the road. They cross the road on their way towards the field, and every evening they cross the road again as they leave the field. So essentially, this is the this is the road, and then the field is obviously inside, and then like the cow will enter in the morning somewhere, kind of graze, and then exit in the evening, like that. So anyway, um, cows are creatures of habit, and they each cross the road the same way every day. So um, if a certain cow enters over here and exits over here, they'll do that in the exact same spot every day. Yeah. Okay. And then next, each cow crosses into the field at a different point from where she crosses out of the field. So they don't like cross into and out of the field on the same point. And all of the crossing points are distinct from each other. So no cow's crossing points are the same. And now Farmer John owns exactly 26 cows, named A through Z, the alphabet, and then so there are exactly 52 crossing points on the road, because each cow has two distinct crossing points, and all the cows um, have different crossing points. So there's 52, two for each cow, and then 26 cows. Okay, so Farmer John records the crossing points by circling around the road, and whenever he comes across a crossing point, he just records which cow the crossing point belongs to. Then he Uh, yeah, okay. Yeah, and so he doesn't record which crossing points are entry points and which are exit points. He just knows they're crossing points, and he writes down which cow they belong to. It doesn't matter with their entry or exit though. Okay, and then looking at the map of crossing points, he's curious how many times various pairs of cows might cross paths during the day. So a pair of cows is a crossing pair if cow A's path from entry to exit must cross cow B's path from entry to exit. We need to help Farmer John count the total number of crossing pairs. So say that we have cow A and we have cow B. Um, Essentially, if cow A and cow B's paths must cross, like there's no way for them not to cross, then they're a crossing pair. Um, and we'll look at how to determine if they're a crossing pair later. Um, yeah, anyway, the input format is just like what Farmer John has recorded, the 52 crossing points, and we have to output the number of crossing pairs. Okay, so how do we determine what a crossing, if a certain pair of cows is a crossing pair or not? So first we have to determine the rules for this. So let's just try and have like a pair of crossing points for two cows, okay? So let's say again we'll have cow A, and let's say cow A enters over here, exits over here, okay? Then we'll have cow B. Let's say cow B enters over here, exits over here, okay? So now you have to think about, do cow A and cow B's paths have to cross? Do they have to cross, or can they not cross? Like obviously you can draw out a path that they somehow cross, but do they necessarily have to cross? Is there a way for them not to cross? Is basically what you have to think about. So in this case, they could cross if you have like if you draw it out like that, right? Obviously they can cross. Like no matter where the crossing points are, there's always a way they can cross. But there's for these cases though, there's also for this case at least, there's a way that they can't cross. So maybe the grazing path looks like that for cow A, and the grazing path looks like this for cow B, okay? Or we could even make it larger, right? Like something like that. Anyway, the point is that these two crossing point pairs don't have to overlap. Okay, now let's look at a different setup of crossing points for the cows. Um, let's say that cow A enters here and exits here, all the way over there. Let's say cow B enters over here and exits over here. So let's say cow A's grazing path is something like this. Okay. Now, obviously, there can be overlap, but there can also not be overlap. Cow B could just stay within this region. So, whatever region that cow A kind of like covered, like, because cow A basically cut a part of like the circle. So whenever a cow goes and grazes, for example, cow A, they kind of like encompass a region of like the circle within like the bounds of their grazing path and the circle's like perimeter, right? So cow B could kind of stay within that area and then like that way not intersect cow A's path, right? So cow B could just kind of stay within this area here. So so yet again, that is not a crossing pair. So again, let's try a different thing. So maybe let's try. So what we've tried so far is like this. We've tried it like this, where cow A and then like has two crossing points, and then cow B has two crossing points. So they're kind of like this, right? We've tried this so far. Um, and we saw that they can just kind of stay in their own separate areas. Now, we've also tried this. We've tried this. We have that and that. So what we saw here when it was like this is that so now B is kind of in cow A's like area, but the actual path does not have to intersect. Okay, so we've tried that. Let's just write down everything we've tried. Um, yeah. So now let's try this. This is the third case. Let's try this. What if something like this? Okay. So you have cow A, cow B, cow A, cow B, like that. So essentially, it looks like this. Okay. So let's say that cow A's path starts here, kind of grazes and goes here. So now one of the one of the crossing points of B is within the area of like cow A's like grazing area, okay? Now the other crossing point for cow B is outside of cow A's little grazing area. So let's say like cow A's grazing area is like over here, right? Like the little area that it kind of contains, right? So now one crossing point of cow B is within that, the other is not within that. So if cow A wants to get from here to over here, it has to intersect. There's no way that it can't. Because it's contained within the area of cow A's grazing like area thing. So it has to intersect if it wants to go and then to its other crossing point and exit. So it turns out that so these are the three cases I think. Yeah. Um, yeah, so these are the three cases, okay? This is case one, this is case two, this is case three. Um, and this one is the only one where the two cows intersect. Now, obviously, the colors can be like interchanged, and it could look something like this. But these are basically the same case. And it turns out this is the only way um, that a crossing pair exists, where they have to intersect, their paths have to intersect. So that makes our problem pretty easy now. We just have to be able to keep track of this, okay? So let's look at how we can solve this, okay? Let's look at the solution to the problem. First of all, here, notice that for the sample input, the sample output is 1, okay? In this example, only cows A and cow B are a crossing pair. So this is if this is cow A and this is cow B again, so you'll see that like if you ignore the other cows, just look at the order in how cows A and B show up. So first A shows up, and then you'll see that B shows up, then you'll see A shows up again, and then after that B shows up. And you'll see this is the and like this is one of the like the this is the case that we were talking about earlier. The only case where they have to intersect their paths. And you'll see it doesn't happen anywhere else, and that's why the sample output is 1. There's only one like crossing pair. Okay. So now that we understand what a crossing pair is, let's think about some rules for the crossing pair, right? So we know that the crossing pair has to show up in this kind of alternating pattern. What does this mean, like, relative to each other, like, in terms of, like, writing it down in code? Or just in, like, numbers, kind of? What does it mean, like, in terms of that, right? So, let's label these, okay? So, cow 1's endpoints, like, let's call them endpoint 1, endpoint 2, so E1, E2, and E1, E2. And you'll differentiate between cow 1's E1, E2 and cow 2's E1, E2 by the color. So, let's say it's like this, okay? Basically, so E1 of cow 1, right, has to be less than the E1 of cow 2, okay? Along with this, along with this, E1 of cow 1 has to be less than E2 of cow 2. And there's one more rule, which is E2 of cow 2 has to be less than E2, or sorry, E2 of cow 1 has to be less than E2 of cow 2. And it turns out these are the only rules for a crossing pair. These are the three conditions you have to check for the crossing pair. So if you have like all four of those like crossing points, and you want to check if these form like if you have the cow and its crossing points, like this is the way you have to check these three conditions to make sure it's a crossing pair. Okay, so now that we understand what a crossing pair is and its rules, also in terms of like variables, like in terms of crossing point and like relative to each other. So we understand all that. Let's actually look at how we can approach the solution. Okay, so there are two solutions. I'll go over the n squared solution first. Um, the n squared solution is that you'll keep track of the ends of the cow's path. So this is basically the cow's two crossing points. Remember, the cows have two crossing points, like that they enter and exit at, and then you have to keep track of that. Okay. It doesn't really matter what path they're in. We always want to assume that they try not to intersect with each other. Remember, and then yeah, because It's a crossing pair only if they absolutely have to cross. Then go through pairs of cows and check if their paths relative to each other allow for crossing. So we're basically what we're going to do is earlier, you know how we like just looked at cow like how we made the three rules, remember? The three conditions on when a cow a pair of cows is a crossing pair. You basically have to look at all the pairs of cows like that, like we just did, and see if those three conditions hold true for all of the cows. So let's go ahead and code our first solution, which is the n squared solution. I did n power 2 instead of n squared. Like I just wrote it as my file name because USACO doesn't accept you can't have symbols in your file name. Okay, so hopefully you have like a clear understanding on what crossing pairs are and their rules. So we can pretty easily code this now. So first, take the input of the string. So string s. Now next, after you've taken the input of the string, you want to have two vectors, and you can call them e1, e2, and they'll both be size 26. And what these are for is, remember earlier when we were referring to the endpoint 1 and endpoint 2 of the like cows when we were like trying to figure out the rules? That's what we're keeping track of here, endpoint 1 and endpoint 2 for all 26 cows. That's why it's size 26. So what we'll do is we'll go from, we're basically going to iterate through the string, and then what we're going to do is this. So if um e1 of for and also what we're going to do is initialize e1 with some like value like -1. So basically if e1 of s of I minus a. So s of I minus a, so you're going to be subtracting like the ASCII, you're going to be doing math on the ASCII values. So si minus a will give you some value from 0 to 25, and that'll give you a position, like an index from 0 to 25 in E1. So that it's gonna basically gonna represent like the position for your letter for this cow. So if this value is equal to -1, that means that we're gonna that means that this is the first time that we've seen this cow. If it's the first time we've seen the cow, that means it's like E1, right? Because it's the first endpoint of for the cow that we're seeing, the first crossing point. Okay, so we're gonna say E1 of S of I minus A is equal to I. Okay, so for example here, when we in the sample input, when we see A, the first character, when we see A, we're gonna see that it's because since vector like E1 has been initialized to -1, we're gonna see that its value is still -1. So then we're gonna change it to I, and I would be 0 in this case. So we'll see that the crossing point, the first endpoint for A is gonna be 0, equal to 0. Okay. Now, otherwise, if the value for E1 and for this cow is not -1, that means we've already seen it before. So now we have to check if the same thing for E2 basically. We want to check if not if it's the first time we're seeing it, but if it's the second time we're seeing it. If it's the second time we're seeing it, that means that this is our second endpoint. So else if E2 of S of I minus A is equal to -1, then e2 of s of I minus a is equal to I. So in the first if statement, we were looking if it was the first time we saw it, and if it was, then we made e1 equal to I. Otherwise, otherwise we're checking if it's the second time we saw it, and then we would initialize e2, or we would make e2 of that index equal to I. So yeah, like e2 of that cow. And then otherwise, if these two conditions are not met, which actually will never happen because you can only see it at most twice. You won't see it a third time. Um, so yeah, it's either the first or the other. So actually, what you can do is actually just put an else on here. This is either going to be the first time you see it, or it'll be the second time you see it, and that's it. Okay. So now once you have that, you've given yourself a way to keep track of the cow's like endpoints. So now let's give ourselves a variable to print at the end, like our as our answer. So the crossing pairs. So we'll initialize it to 0. And now remember, our approach was to iterate through all pairs of cows and see if they work. So I equals 0, I less than s dot size equals plus, or sorry, not s dot size less than 26. 26 j plus plus, right? Because 0 to less than 26 because we're going through all the cows. So it's choosing the first cow, choosing the second cow. Okay, and now remember our three conditions to check if a pair of cows is a crossing pair or not. So if e1 of I, so if the endpoint 1 of the first cow is less than the endpoint 1 of the second cow, and the endpoint 1 of the second cow is less than the endpoint 2 of the first cow, and the endpoint 2 of the second cow, or no, of the first cow is less than the endpoint 2 of the second cow. If it meets these three conditions, then we have ourselves a crossing pair. So let's do pairs plus plus. And then at the end, you just want to see out pairs. And this is file input. So query open circle ross.in read stdn circle ross.out stdr. And I have those files over here already. And yeah, we can go ahead and test this. So for circlecross.in, I already put the input in there. We can go ahead and run the program and see if we get the correct output. Let's just let it run. And yeah, so that was all for like the n squared solution. So as you can see, we got 1. So now we can go test it. Circle cross here. N power 2.cpp. I have to log in again. Probably got logged out. Yeah. So the n to the fourth solution is that you're basically going to take advantage of some things. Like you're just going to take advantage of the fact that n is really, really small, and you're going to use that in a way. So first let's submit this. Um, yeah. So yeah, it's done. And yeah, this is all you need to do for the n squared solution. Now let's move on to the n to the fourth power solution, like O of n to the fourth power. Um, yeah, so like as I said, you're gonna take advantage of the fact that n is a really, really small value. N being like the size of the string, like the string that Farmer John creates. Okay, so essentially in the n squared solution, what we were doing, we kept track of the endpoints of each cow, and we went through each pair of cows and checked if their endpoints were able to match up to make a crossing pair. In this solution, what we're going to do is we're going to iterate through every set of four crossing points and see if they're made up of two cows, if they're made of two specific cows, right? Because if we take a set of four endpoints of four crossing points, that means that since each cow has two crossing points, it could be made up of two specific cows. It could be made up of three cows or four cows, which we don't know. Um, like the edges could come from two, three, or four cows. No, sorry, not the edges, the crossing points. Okay. So here, so essentially what we're gonna do is remember our sequence, right? Like we had to have like an alternating sequence of crossing points, right? For it to be a crossing pair. Essentially, we're going to try to force that sequence, right? We're going to try and force the sequence of things. So basically, for this n to the power 4 solution, we're going to choose crossing points and we're going to try to force it to alternate. So what we're going to do is the first crossing point that we choose, we'll label it E1, okay? E1 of the first cow, let's say. Then the second crossing point we choose, we'll label it E1 of the second cow. Then the third crossing point we choose, we'll label it E2 for the first cow. And the last crossing point we choose, we'll label it E2 for the fourth cow. Now you'll see that when we try to force it in this way, our our points are already arranged in the wanted arrangement to be a crossing pair. All we have to do is that after we check this, if the crossing points come from two cows, that means that they're already in this arrangement, okay? Um, so yeah, like if they come from three or four cows, like maybe this edge came from a third cow instead of um the second cow, okay? Maybe it came from a third cow. That could be possible. But all we have to check here is that once we force this kind of combination, we just have to check if these actually do come from just two cows. Okay, so let me show you how that would work. So for so let's call this, um, so let's say we have cows X and Y, okay? We're imagining that we're having cows X and Y, okay? So we'll call it, instead of E1, like since like we don't have colors to differentiate, we'll just call it X1 equals 0, x1 less than s dot size. And now we're going to use s dot size because we're going through every single crossing point. We're not going through the cows, we're going through the crossing points. Okay, then x2 sorry, x1. And then for, so here we've chosen the endpoint, um, the endpoint 1 for the first cow. Then we're going to choose the endpoint 1 for the second cow. And remember, to ensure like this alternating pattern, we have to make sure that the endpoint 1 of the second cow comes after the endpoint 1 of the first cow, so x1 plus 1, then y1 less than estimate size, y1 plus plus. So basically, in the n squared solution, remember our last step was to check if the crossing points of the two cows matched those three conditions, and then we would say that this is a crossing pair. Essentially, what we're doing is here, we're forcing the three conditions to be true, but we don't know if they actually come from two cows. And that's what we have to check at the end. So next we'll check endpoint 2 of the first cow is equal to endpoint 1 of the first cow plus 1. And then this can go up to less than s dot size, x2 plus plus. And then yeah, endpoint 2 of the first or of the second cow equals x2 plus 1, and this has to be less than s dot size, and then y2 is plus. Okay, so I hope this makes sense, right? So look at this. When we choose endpoint 1 of the first cow, we initialize endpoint 1 of the second cow to be endpoint 1 of the first cow plus 1. Okay? So that ensures that the endpoint 1 of the second cow comes after the endpoint 1 of the first cow. Then this over here, y1 plus 1, this makes it so that the endpoint 2 of the first cow comes after the endpoint 1 of the second cow. Then this here makes it so that the endpoint 2 of the second cow comes after the endpoint 2 of the first cow, okay? So you'll see here that by how we initialize our nested loop pointers, that's essentially forcing those three conditions of a crossing pair to be true. Now what we have to check is that are these four crossing points actually from a pair of cows, okay? So essentially if s of if s of x1 is equal to s of x2 and s of y1 is equal to s of y2, then pairs plus plus. Okay, so here, by how we initialized the pointers of each nested loop, we ensured that the three conditions for a crossing pair were met. Now here, we're checking, are they actually a pair of cows, okay? Are they actually a pair of cows, or is it like some more than that, okay? Um, if s of x1 is equals s of x2, this is basically saying like these are two endpoints for one cow. So is the cow at these two locations in S actually the same? And the same thing for the second cow's like endpoints. Okay? If that is true, then that means they're actually a pair. So if they are actually a pair, we've already met the conditions for crossing pairs, so just do pairs plus plus. And then output pairs at the very end. And again, this is also file input output. So here is our input. Now let's run the program. Mhm. And yeah, so we got 1 as our output. Okay, so now let's try and submit it. The input 4.cpp solution. And yeah. Okay, and you'll see here that for the first problem, the test cases took like 2 milliseconds each. And you'll see for the second problem, it's the same. They took around 2 milliseconds each. This is just because um n is just so small that like even n squared to n fourth was not that big of a difference. It wasn't that significant because n was just so small. It was just um like maybe around 52, something like that, right? So it's just too small to make a difference. Yeah, I hope those explanations were clear for those two approaches. I hope those two approaches made sense. And I hope this problem made sense. And yeah, so just keep practicing, I guess, and I'll make videos in the future about more problems, computer competitive programming problems. And yeah, I hope this was helpful. Bye.